All right, let's just jump right in. When you picture a fighter jet or maybe a Formula One car, you're probably thinking about that sleek, finished product, right? But the real magic, the stuff you never get to see, that happens way, way before. So today, we're going to pull back the curtain on this hidden, super high stakes world of composite tooling. It's really the foundation of all high-tech manufacturing.
$1,000,000. Just let that sink in for a second. And no, we're not talking about some fancy supercar. This is the price tag for a single piece of equipment, just sitting on a factory floor. So what in the world could cost that much?
And that's the big mystery, isn't it? This $1,000,000 thing. It's not even part of the final plane or car. It never leaves the factory. It never gets sold. It's just this huge investment that sits there, doing its job again and again and again. Any ideas what it could be? All right, the answer? It's the composite tool. Think of it like a mold, but a super advanced, insanely engineered mold. Every single carbon fiber wing, every one of those slick monocoque chassis for a race car, it was born inside one of these things. It's honestly the unsung hero of the whole process. And today, we're going to give it the spotlight it totally deserves. So, before anyone even cuts a single piece of metal or lays down a strip of composite, engineers are faced with these huge choices. And these decisions, they literally determine if the final part will be a success or a total failure. The tool's design, it's everything. So the very first big question for the engineers is this: what are we optimizing for? Do we need a perfect inside surface or a perfect outside surface? See, if you go for the inside, that's called IML, your parts are going to fit together like a dream during assembly. But if you focus on the outside, the OML, that's how you get that flawless, super slick aerodynamic finish. It's just a classic engineering trade-off, Form versus function, right from the get-go. And believe me, it only gets more complicated from there. Just take a look at the to-do list for one of these tools. It's got to stay stable at like 350 degrees Fahrenheit, handle crushing pressure, heat up perfectly evenly. Oh, and it has to resist wear, be super smooth, and be machined with insane precision. And that's not even the full list. It's just a monumental challenge for any engineer. Okay, so that brings us to the materials. Deciding what to make the tool out of, it's like a battle of titans. Each material has its own personality, its own strengths and its own deadly weaknesses. This hunt for the perfect tool material, it's been going on for decades. We started with the old standbys, steel and aluminum. Then, in the early 80s, we got a little fancier with stuff like nickel. By the mid-80s, we had this wild idea. Hey, let's make composite tools to build composite parts. And then the 90s came along and brought us the age of superalloys like Invar. So first step in the ring, our old friend, steel. Just think of steel as the reliable, tough-as-nails workhorse of the factory floor. It's been around forever for good reason. So on the plus side, steel is cheap, and it is unbelievably durable. We're talking it can survive over 1,500 trips into the oven. But the downside is huge. It's crazy heavy. It heats up so slowly in that big industrial oven, the autoclave. And here's the kicker. It expands a lot more than the carbon fiber part that's curing inside of it. All right, next up we've got aluminum. This is the speedy, lightweight challenger trying to fix some of steel's biggest flaws with pure agility. And with aluminum, the trade-offs are pretty stark. It's light, which is great, and it heats up super fast, which saves a ton of valuable time in the autoclave. But it's soft. You can damage it really easily. And that thermal expansion problem, it's even worse than steel's. For parts that need to be super precise, that can be a total deal breaker. And then, someone had a really clever idea. What if we made the tool out of the exact same material as the part we're trying to make? And just like that, composite tooling was born. The clever mimic. Now, on paper, this is the perfect solution, right? A carbon fiber tool making a carbon fiber part, they should expand and shrink at the exact same rate. It's genius. But in the real world, after you heat it and cool it over and over again, the tool's resin starts to get these tiny little micro cracks. And those cracks lead to vacuum leaks, which can totally ruin the part you're making. So they're just not quite durable enough for really high volume production runs. And that brings us to the modern champion of tooling materials, Invar. This is the super expensive, high-tech alloy that pretty much solves the single biggest problem of all. So what's its superpower? It has an incredibly low rate of thermal expansion. Invar barely grows or shrinks at all when you heat it up, which means it almost perfectly matches the composite part. It's basically the holy grail for dimensional stability. But of course, that kind of performance comes with a superstar price tag. It is extremely expensive and a real pain to work with, which means it's usually saved for only the most critical, top-tier jobs. So, as you can probably tell, all of these material choices really boil down to one central problem: thermal expansion. This is really where manufacturing stops being just manufacturing and becomes a high-stakes war against the laws of physics. It all comes down to this one little property called the coefficient of thermal expansion, or CTE for short. Every material has one. A high CTE just means it expands a lot when it gets hot. A low CTE means it doesn't. And when your tool and your part have different CTEs, you've got a massive problem on your hands. Okay, so let me walk you through how this goes wrong. At room temp, everything's great. The part and the tool fit together perfectly. Then you heat them up in the autoclave. The metal tool, with its high CTE, starts to expand, a lot more than the composite part inside it. But the real danger? That comes when it cools down. The tool starts to shrink back, and because it grew more, it shrinks more. And it puts this immense, crushing pressure on the finished part. It's literally trying to squeeze it to death. So to get around this, engineers have to pull off this incredible trick. They have to calculate exactly how much the tool is going to shrink, and then they have to intentionally build the tool slightly smaller at room temperature to compensate for it. And if their math is off by even a tiny fraction of a millimeter, the results are, catastrophic. And when I say catastrophic, this is what I mean. Your final part can come out the completely wrong size. The delicate layers of the composite can literally pull apart. That's called delamination. The whole thing can just warp out of shape. And at the end of the day, you're left with a piece of junk. A scrapped part that's worth thousands, sometimes tens of thousands of dollars, all because the tool and the part got into a fight with physics. Which brings us right to the main takeaway here. The tool isn't just some accessory in the process. It's not just a mold. It is the literal foundation that the quality, the precision, and ultimately the safety of the final part is built on. And this quote from the source material really just says it all. It's always tempting to try and cut corners, right? To save a few bucks on these huge one-time costs. But trying to cheap out on tooling, that is the absolute definition of false economy. A bad tool is just going to cost you way, way more in scrapped parts and endless production headaches down the road.
So I want to leave you with one final thought. As we keep pushing for lighter, stronger, more complex parts for everything from jets to race cars, maybe the real innovation isn't in the final product you see. Maybe the true genius is hidden away on the factory floor, inside that unsung hero that makes it all possible in the first place, the tool itself.